Hello, I am Harshil Jain, a senior undergraduate in computer science and engineering at IIT Gandhinagar, and I will be presenting my work on end-to-end binarized neural networks for text classification, which I did as an internship at NeuralSpace during the summer. This work got accepted at the Sustain NLP workshop at EMNLP 2020, one of the premier conferences in natural language processing across the globe. So coming to the main idea, recent advances in deep learning have led to a significant performance increase on several NLP tasks. However, the models have become more and more computationally demanding. The state-of-the-art transformer models are a good example. In this work, we introduce a fully end-to-end binarized neural network architecture, which are for the task of intent classification that uses binary representations followed by a binarized classifier. So coming to the Ngram statistics. So let's take the example of supervised learning. A dataset consists of samples and their corresponding labels. For each sample, we normalize the samples and create tokens. An n-gram vocabulary is created for each token, where n can be any positive integer. A value of 2 to 4 works well in real life and is used in our experiments. With the created vocabulary, we vectorize the vocabulary to obtain the feature representation of each sample with vector size equal to the number of n-grams. This is shown pictorially in the slide shown. Now coming to the embedding into the hyperdimensional vector. So we assign each symbol with a random d-dimensional bipolar HD vector, and these vectors are stored in a matrix which is denoted by H, which is referred to as the item memory. So first H is generated for the alphabet, and the position of the symbol SI is generated by applying permutation to the corresponding HD vector I times, and a unique HD vector is then formed for each n-gram vocabulary using the binding and permutation operation as shown in the right. It is worth mentioning, however, that intuitively the entire approach works because the embedding is done in such a way that in the projected high dimensional space, the two similar n-gram statistics still remain very similar. Now, binarized neural networks. So once we have the binarized embeddings, we use a binarized neural network as a classifier, and we constrain the weights and activations of the network layer to be either +1 or -1. We use a sign function for that. For all the values greater than or equal to 0, we get +1 as output and -1 otherwise. This is stated in the formula below. Now coming to the entire end-to-end binarized pipeline. So let's look at the final proposed pipeline. We get the input text document, we do some pre-processing over it, then we tokenize the input document using the Ngram statistics. We construct the count-based vectorizer, and we embed the tokens into a binarized high-dimensional vectors. And finally, HD vectors are used with the binarized neural network as a classifier to classify the intent. Now, the datasets used for evaluation are 3 small datasets with 2 to 8 intent classes and 1 large dataset with 20 intent classes. The training and test sample vary a lot, and the dataset is chosen to show the applicability of our methods on small as well as large datasets. The smaller dataset is limited to 3 training samples, while the large dataset uses 11,500 samples to train. Now coming to the results. So if we compare the results of other platforms to our binarized architecture, we see that we achieve near to the state of the art compared to other platforms. And we can thus show that our method performs equally well compared to other platforms. Now coming to the comparison of the normal BNN architecture with the fully binarized architecture, we can see that most of the times the fully binarized architecture achieves greater F1 scores for most of the data sets as compared to the non-binarized version of the architectures. Now we also performed ablation studies to confirm that the HD vectors perform well or worse compared to GLOW or SEMhash. And we found that the binarized hyperdimensional vectors performed well on 3 datasets and performed equally well on the other dataset. So we thus prove that the binarized hyperdimensional vectors are useful as embeddings for all the 4 datasets. Now coming to the primary reason for the paper, the memory comparison. So we show that the binarized hyperdimensional vectors use about 20 to 40% less memory as compared to their non-binarized counterparts on all 4 datasets. And the training time comparison for all 4 datasets. So we can see that we achieve a 1.5x to 2x gain per epoch when we train the binarized version of the architecture using the binarized embeddings for all 4 datasets. So we can show that we achieve efficiency both in terms of memory and training time when we use this fully binarized end-to-end pipeline for the task of intent classification. Thank you. The paper can be seen here, which is published in ACL Anthology.